Hi, my name is Takhya Holley, and I am a first year graduate student in Dr. Peter Kroll's lab. And today I will be doing a presentation over the kinetic analysis of a cross-linked polysiloxane. And so, silicon oxycarbide is derived from organopolysiloxanes that are cross-linked or by the sol gel technique. They have applications in lithium anode materials, temperature and pressure sensors, fibers, and aerogels. Isoconversional model fitting and decomposition analyses are used to determine the kinetic triad to better understand the processes occurring during the heating of the material. The motivation for this process is to learn about the synthesis of PMHS cross-linked with DVB and understand the processes and use as a model system for further methodology development that can be applied to other systems. For the synthesis, we use 5 ppm platinum catalyst relative to the polymethyl hydroxysiloxane. Mix it with 100% DVB by mass, stir for 10 minutes, and then added the PMHS DV dropwise while stirring. Stir for an additional 10 to 15 minutes and let the sample sit overnight at room temperature. The sample was further heat treated at nitrogen the following day at 120 degrees Celsius for 12 hours, then ball milled, resulting in the white powder on the left. We are using thermogravimetric analysis techniques for our analysis, and we are using a sample size of 5 to 6 milligrams in 90 microliter aluminum crucible. We do a 30-minute purge in nitrogen, and then we ramp to 1,000 degrees Celsius using the heating rates of 2, 3, 5, 7, 10, 15, 20, 30, and 50 degrees Celsius per minute. We use the isoconversional kinetic method for a single step process to start with, so that we learn about the multi-steps kinetics, about the treating it as one overall process initially. And then with that, we will take the TGA, convert it into degree of conversion data, which is the alpha T plot. On the right of that, we then take the derivative where we have the d alpha dt. From here, we can observe that we have more than one process. We have about 4 processes that we can see from the derivative. For the second equation, which is the Friedman method, we take the natural log of the d alpha dt and we graph that versus inverse temperature in Kelvin. And we use the slope of the lines to determine the activation energies, where for the overall kinetic analysis, we are seeing activation energies of about 220 kilojoules per mole. Then we, now that we have a estimate of the activation energies for the overall process, we move on to the decomposition of the processes using a Fraser-Suzuki function, which is a modified Gaussian function that allows for us to account for the asymmetry of the peaks. So we have this here with the 2 graphs on the left where we see the decomposition for the 4 processes for 2 different heating rates. And then we use the decomposed processes, do the integration, and simulate back out the alpha T curves, which are the bottom graphs where we see process 1, 2, 3, 4. And where we see that process 1 is contributing about 3% to the overall. Process 2 is 50%, process 3, 32%, and then process 4 is counting for 15% of the overall. Where we have the residual sum squares on the right, which are about 1% or less. The results of the kinetic analysis, now that we have decomposed the 4 processes, we do the Friedman analysis again, and we determine the activation energies for each one of the processes, going from the first process is on the bottom to the 4th process is on the top. We know that the second process is the dominating process, and it is the one where we have a characteristic asymmetry parameter of negative 0.3. So we know that this one is a F1 or a first order reaction with a activation energy of about 220 kilojoules per mole. The other 3 processes are tentative. We cannot say definitively that they are 4th order, 3rd order, or a 3D diffusion model. For our future work, we would like to change the mass ratios and also change the mesel porosity of the system and develop these analytical tools further. And in summary, we have done a thermokinetic study of the model system. We have done multi-process analysis using peak fitting, determined the activation energies for each one of the individual processes, and found that the dominating F1 process has an activation energy of 220 kilojoules per mole. Thank you.